the application that I want to show you is an application that deals with rational expressions rather than a rational equation. And where I have seen it come up is in a perimeter and an area question. Okay, so for example, if I gave you a rectangle and I said that the side length of the rectangle, let's say the width is 2 over 3x squared, and I said that the length was 1 over 9x. Okay, so what I'm doing is I'm looking at rational expression dimensions of a rectangle. Okay, I've seen a question very similar come up at least twice. You could be asked for an expression for either the perimeter of the rectangle or the area of the rectangle. Okay, so let's remind ourselves, how do we figure out the perimeter of a rectangle? Yeah.
It's just side plus side plus side plus side.
Yeah, we add up all the sides. Or you could think of it as what's 2 widths plus 2 lengths, or 2 lengths plus 2 widths, right? So you need to know that. That's considered pre-knowledge. Perimeter equals 2 length plus 2 width. So if we were asked for an expression for the perimeter, we would have to add up 2 times 1 plus 9x plus 2 times 2 over 3x squared. Okay, this is a rational expression addition problem. So this is actually the biggest step, just being able to develop your own expression. Okay, now we have to simplify it. So where would you go next? What's the next thing you would do? Yeah.
Apply the 2 to the fraction.
So we need to multiply the 2 to the rational expression. Now here's another mistake that I often see people do, is they'll say 2 times 1 is 2, 2 times 9x is 18x. So this is 2 over 18x. Why is that wrong? Yeah.
Because 2 is the same thing as 2 over 1.
Exactly. Yes, 2 is 2 over 1. So this is actually 2 over 9x plus 4 over 3x squared. Okay? Now, what would you do next if we want to add these two expressions together? Yeah? Yeah, you need a common denominator. So let's think about this. Between the 9 and the 3, what's the LCD of 9 and 3? 9. And then between x and x squared? X squared. Right? And you can think of this as 3 times 3 times x. And you can think of this as 3 times x. Right? So in the LCD, you have to be able to see every single factorization of each denominator, but you don't want anything extra. So if you write out the 3 times x, from the first denominator, I've got the 9x covered. And then if you compare and say, OK, do I have a 3? Yes. Do I have an x? Yes. Do I have a second x? No. So I have to add that in. OK? All right. And by the way, figuring out the least common multiple of several numbers works exactly the same way if you use prime factorization. OK, so we need our LCD to be 9x squared. What do I need to do to this first rational expression to achieve that?
Times x over x.
Yeah, multiply by x over x. And this guy? 3 over 3, right. So this is going to end up being, now our whole denominator is 9x squared. This is 2x, and then plus 12. Okay. Now the only other thing that we might be able to do is see if we can factor the numerator and cancel. And the numerator does factor in this case. You can factor out a GCF of 2. So you could try that, but if you can also see, okay, well, if there's a 2 on the outside, still not going to cancel with anything in the denominator, then you can kind of skip that step. Okay? Now, the other thing that I want to talk about, though, are non-permissible values, because when you're talking about an application, it's very similar to when we were talking about applications of relations and functions. Okay? Now, if you're just talking about any linear function, let's say, right, straight line, the domain and range are everything. X can be anything. As soon as you restrict, or as soon as you impose a context into that situation, you may have to limit the domain and range. Because, for example, it may not make sense to have negative values. Okay? If you're talking about a linear function being like, what's the total cost of X number of t-shirts and they cost $15 each, you can't have negative t-shirts, you can't have negative costs. So you may have an equation that has a domain of everything and a range of everything, but you'd have to restrict it in that specific situation. Okay? Now let's think about this. If we were just considering this as a rational expression, what would the non-permissible value be? Yes. If this was just a rational expression, that's the non-permissible value. Okay? However, this is a context. So think about lengths and widths and what type of numbers you're allowed to have for lengths and widths. Can it be any number that exists in the world?
It can't be negative.
Exactly. It cannot be negative. So we actually have to put in more information around our non-permissible value here. And it can't be 0, but it also can't be negative. So we would have to say that X is greater than 0. It's positive. And that incorporates the non-permissible value of 0, because if X is positive, it can't be 0. But it also throws out all of those possibilities of having a negative side length. Okay, so that's another extra layer that we have to think about. Okay, so with these expression questions, I've seen ones where you have to figure out the perimeter. I have also seen ones where you have to figure out the area. Okay, so let's just remind ourselves of that as well. Area of a rectangle, how do we get that? Length times width. Okay, so if you're figuring out the area of this rectangle as a rational expression, you would go the length is 1 over 9x times 2 over 3x squared. And that's just 2 over 27x cubed. Okay, so that's all we can do here because there's nothing to simplify. There's no common factors in the numerator and denominator. Okay, but I have seen a question like this come up, and this is kind of the only one that I've seen that is an application of a rational expression where there is no equal sign in there. Okay, so I wanted you to see that because it's not something that I had put into my notes. Okay, so far so good? Okay. So before we actually get into the applications that we're going to look at in detail, which usually involve equations, I want to talk first about what type of situation could we use to model, could we use a rational equation rather to model. Okay? So think of the structure of a rational expression. What does it look like to you? How would you describe it? Rational expressions, polynomial over polynomial. If you were to say it kind of looks like this, and don't say it looks like a nightmare, although you may think that, right? Think of how would you relate it back to a number? What would be an analogous number if you were to compare a rational expression to a number? What type of number would that be? I heard someone say it. Rational, yes, a fraction, yes. Okay, a rational expression is like an algebraic fraction. Okay, so typically these applications have to do with something where we're doing like a division. Okay, now I'm also going to remind you guys of something that you probably haven't thought about in several years, but that will become really important in this unit. So does anyone remember what a ratio is and what a rate is? Or maybe what the difference is? Okay, do you remember ratio?
Like 1 to 2.
1 to 2, 2 to 1, yeah. So you might say like the ratio of the side length of a rectangle, the width to the length is 1 to 2, right? Something like that, yep.
Right, like how much something increases?
Okay, so let's step away from math class for a second. You guys probably, like in your everyday life, hear about rates. If you read the financial section of the newspaper, you hear about rates. But there's rates all over the world. Like everywhere you look, there's going to be a rate. When I drive to work every day, I probably see 8 rates as I'm driving on the road. Okay, so I want you to think, can you think of an example of a rate? What's that? Speed, yes. Speed, if you think about the units of speed, of a speed limit, what would those units be? Kilometers per hour. What does the word per mean in math? Yeah, so okay, we're almost there. Let's just think about the word per. If I said 5 cookies, or let's say 10 cookies per two students, what would you think about doing there mathematically? Yeah, division. Yeah, so the word per means division. Okay, so a rate, now let's get to a ratio versus rate. Okay, a ratio, because you may not remember this, and it's probably something that you haven't seen in a long, long time. Ratios and rates are both numerical comparisons. So we are comparing two numbers. A ratio is a numerical comparison between two values that use the same units. Okay, so I may say at Central, there are 600 grade 11 students to 700 grade 12 students. The units are always the same. It's the number of students. Or if you're comparing a width to a length, the units are the same. They're going to be a unit of length, right? Maybe centimeters, maybe meters, whatever. A rate, on the other hand, is a numerical comparison between two numbers that use different units, like kilometers per hour. One unit is distance, the other unit is time. Okay? Now, because a rational expression looks kind of like a fraction, the units that we might see when we're thinking about modeling an equation with, or a situation with a rational equation, are ones that include rates. So almost all of these examples will include a rate, okay, where you are comparing two things with different units. Often it's speed. Speed is a comparison of distance covered over a certain period of time, but not necessarily. If you go to the supermarket, you see rates all over the place, right? Apples are $2 a pound, $2 per pound. That's a comparison of $2 per 1 pound of apples. Okay, so almost everything that we're going to do with these equations will involve rates. Okay, we kind of already talked about non-permissible values in the previous example, but what I'd like to say here is that when we're solving an application problem, we have to think about non-permissibles, but we also need to consider what values make sense in the context of the problem. And more often than not, we need to exclude the negative values. Okay, so in an application, in addition to NPVs, we also need to think about what values make sense in the context. Okay? So for example, if you are looking at covering 20 kilometers in X amount of time, an expression for your speed would be 20 over X. 20 kilometers per X amount of time. Okay? That would be a situation where X would have to be greater than 0. Your time must be positive. Okay? So I'm actually going to skip this first example because I don't actually think it's a very good one. I'm going to take it out next time. And we're going to move on to number 2. And essentially what we're going to do in this section of this unit is look at a whole variety of questions, because what you will see is that there are only so many types of questions that involve rates. And so we're going to look at a whole variety of them, because once you see a couple of them, they tend to get repetitive. And that's kind of what you want to do when you're studying, is kind of keep practicing until you're like, oh yeah, I've seen that before. This looks familiar. I know what to do. Okay? So let's look at this question first. Okay? When they work together, Stuart and Lucy can deliver flyers to all of the homes in their neighborhood in 42 minutes. If Lucy works alone, she can deliver the flyers in 13 minutes less time than Stuart can when he works alone. Okay? The table below represents the information, and we're actually going to fill this out together. Okay? And we are told if the equation 1 over x plus 1 over x minus 13 equals 1 over 42, where x is greater than 13, represents the situation, determine how long it takes for Stuart to deliver the flyers alone. Okay? Now, I think before I get into this question, sorry, I know I'm going a little out of order. I want to just show you guys something. I want to ask if you've ever seen this before in science class. Yeah? Okay, so this triangle is just a graphic way of remembering the relationship between speed, distance, and time. Right? So if you think about it, speed is equal to distance over time. Time is equal to distance over speed. And then distance is equal to speed times time, because they're beside each other. Okay? You can kind of generalize this in the same way with a rate, where this guy's your rate, just like speed is a rate. Okay? And then these two are going to be the 1 unit per the other unit. Usually we think about how much work is getting done, how much are we buying, that sort of thing. So I'm just actually going to write the amount of work divided by time, because this is often what we see, but sometimes work and time can be interchanged with something like, if it's a unit rate for you're buying something from the store, it might be dollars per pound, where this is money, this is mass, right? So, but this is kind of a little bit more general in that if you're thinking about the rate at which something is going to get done, that's equal to how much work did you do? How much has been done divided by the amount of time that it took to do it. Okay, so for example, if you can, this is kind of obsolete at this point, but when I was in high school, it was almost always, how much can you type per minute? How many words can you type per minute? Right? So that's a rate. How much work is getting done is how many words are you typing per time per 1 minute. Okay? Okay, so let's go back to this example. Now, one thing that's really helpful to think about when you're working through these problems is what is being asked for. At the end of the day, we're asked to determine how long it takes for Stuart to deliver flyers alone. Okay? So the idea here is that Stuart delivers flyers. Is it Lucy? I think Lucy. Lucy delivers flyers. If they work individually, this is how long it takes them to deliver all the flyers. If they work together, they can do it in 42 minutes. Okay? when you're being asked a question, essentially you want to identify, we're going to have to introduce a variable here. We have to introduce a variable because there's something that we want to find out. Okay? So what we want to find out is how long does it take Stuart to deliver the flyers alone? When you are working on these types of problems, you kind of want to make a table where you can track these three things: the rate, the work, and the time. And often if it's two people, there will be two parts to the problem, right? It might be two different people doing work. If it's a speed problem, you may be tracking how long does it take to get to one place, and then how long does it take to get home. So you'd be tracking two parts of the journey. But there's often two parts involved. Okay? So you want to create a chart where in the rows you have the two parts. In this case, it's Stuart and Lucy. And in the columns, you're tracking these three things: the work, the rate, and the time. Okay? And the general rule of thumb is that you have to introduce a variable somewhere. And the best place to introduce a variable is for the thing that you're trying to answer, which is how long does it take Stuart to deliver the flyers alone? So that would be Stuart's time. So what I'm going to do is I'm going to make Stuart's time the variable, because that's what I'm trying to figure out. Okay? Now, as soon as you assign a time to Stuart, or to one piece of it, you want to try and use information in the question to figure out an expression for Lucy's time using that variable x. So let's look at the information that you have, read through it, see if you can tell me something in there that's going to relate Lucy's time to Stuart's time. Yeah? Okay, tell me where you see that in the wording of the question.
Well, if Stuart's working, or delivery time working alone is X, and Lucy, when she works alone, delivers in 13 minutes less time than he does.
Exactly. Yeah. So Lucy's time is 13 minutes less than Stuart's. So if his time is x, her time will be x minus 13. Okay? So one piece of the chart you need to figure out by defining a variable and then using that same variable for the other person. Okay? Another piece you should be given. Now, this is where this example is kind of tricky, and if you've never seen this before, you kind of have to know it, which is how much work is getting done here. We don't know how many flyers there are. We can't say that one job is 5,000 flyers. We're not given that information. But what we can assume is that they're both doing the entire job. So we're going to say that the amount of work that's being done is one job. One job of delivering all the flyers. Okay, now that is really a tricky part to this. That's the hardest part to these types of work questions. And that's why really we're going to go through a whole variety of different questions that you guys can kind of see maybe what to look for. Okay, so the rule is in one column, you introduce a variable and fill that column out using that variable. In the other column, you should know that from what's given in the question. In the third column, you need to use this relationship and the other two variables to get the third column. So deliveries per minute is rate. Okay? Rate is amount of work divided by time. So Stuart's rate is 1 over x. Lucy's rate is 1 over x minus 13. Okay, so in these charts, you're going to look at the two pieces, and you're going to look at time, amount of work, rate. You fill two of them out by yourself, and you use the other two columns to fill out the third. Okay? Now this may seem kind of weird to think about, the rate is 1 over x. But let me kind of put it this way. Let's say that you complete one math test in 60 minutes. Your rate per minute is you're doing 1/60th of the test per minute. Does that make sense? So over the course of 60 minutes, you do 60/60ths of the test, which is the entire test. Okay, so that's where this comes in, that 1 over x. Okay? Once you get this chart, you need to say, okay, there's got to be some other information in the question that I haven't used yet. And you're going to use that information to create an equation. So what is the piece that we have not incorporated into the table yet?
42.
Yeah. When they work together, their combined rate of working is going to be equal to the sum of their two rates. That should equal 1 job per 42 minutes. So when you look at this equation, and in 30-2, most of the time the equation will be given to you. There will be times when you have to come up with it yourself, but that's a standard of excellence question. So most of the time, the equation will be given to you. If you look at this equation, 1 over x plus 1 over x minus 13 equals 1 over 42. In English, what this means is Stewart's rate plus Lucy's rate equals their rate together. That is sort of the English, the half English, half math equation. Okay? Now we also have this restriction over here that says x has to be greater than 13. So tell me about that. Why does that make sense? Yeah?
Because if we look at like Lucy's rate, she can't deliver it at 0.
Yeah, exactly, right? So if you look at the time, both times have to be positive. So in order to make Lucy's time positive, her time, the x value has to be greater than 13. Because if it's less than 13, then her time will be negative. So this is to ensure that both times are positive. Okay? So once we have an equation, and I like to talk through the why of every equation for a couple of reasons. Number one, if you don't know why an equation makes sense in modeling a situation, you are going to be very detached from what the solution actually means. So you may be able to solve this, you may get an x value, but you're going to have a really hard time connecting that x value back to the situation. That's number one. Number two, next week we're going to create the equations ourselves. Okay, so we have to go through this anyway. Okay, so once we have the equation, though, all we need to do is solve it. So we need to think about this as a rational equation. With a rational equation, first thing to do is factor. Is there anything here to factor? No. Okay. Next thing is LCD. So what would the LCD in this equation be? There's 3 denominators. They're all factored. Are any of them identical? No. So what's the LCD going to be?
42 times x minus 13.
Exactly. It's all of them multiplied together. 42. I'll switch back to black, actually. Except I don't want it to be that thick. Okay. Once we know the LCD, we can multiply everything by that LCD. So I'm going to actually rewrite this a little bigger, because it's going to get all squished here. Or maybe just a little bit more spread out. And I'm going to multiply this by 42x times x minus 13. And I'm going to multiply this by 42x times x minus 13. And I'm going to multiply this by 42x times x minus 13. Okay? And then all of my original denominators will cancel. So in the first term, the x's cancel. And I'm left with 42 times x minus 13. In the second term, the x minus 13's cancel. And so I'm just left with plus 42x equals, over here the 42 cancels. So I'm left with x, or 1 times x, which is this x, times x minus 13. Okay? All right, what do we do now? Yeah, so we got to expand everything, right? Because this is going to be either a quadratic or a linear equation, and now we have to solve that. So if I expand here, I'm going to get 42x minus, what is this, 500 and something? 546, thank you. Plus 42x equals x times x is x squared minus 13x. Okay? And I'm just going to simplify the left side again. So 42x plus 42x is 84x minus 546 equals x squared minus 13x. Okay, what type of equation is this? Quadratic, yes. So how do we solve that? What's the next thing we need to do? Yep. Right, make one side equal to 0. And I don't know if this is just habit, but I always like to keep my x squared coefficient positive for some reason. So I usually move things accordingly. So I'm going to make the left side 0. But you could make the right side 0 as well. It doesn't matter. So I'll subtract 84x and add 546. Okay, so this is 0. This is x squared minus 97x plus 546. Okay, now what? Yeah, quadratic formula. So you may want to try factoring this, but I'm someone I'm not trying to brag, but I think I'm pretty good at factoring. I wouldn't bother factoring this myself, because when I look at this, I think to myself, if I tried to factor, I would be very inefficient. So even if you're good at factoring, you always still want to think about what's going to be the fastest way. And it's okay to mix and match your strategies so that you're trying to think what's fastest and what's going to get me the right answer. Okay, so my A value is 1. My B value is negative 97. And my C value is 546. Okay? And my quadratic formula is x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay? And I like to use these brackets so I don't make sign errors. So I know my b has to go here, negative 97, and here, negative 97 squared. My a value is 1. That goes here and here. And my c value goes here, so 546. Okay? And when I'm evaluating these personally, I do the piece inside the radical first, the b squared minus 4ac. That's called the discriminant. If you remember from 20-1 and 20-2, it tells you how many solutions you have, actually. Okay. So you guys can do this too so that you can make sure I'm not making any mistakes. So b squared minus 4ac, make sure to enter it as you see it, meaning the negative 97 should be in brackets. B squared minus 4 times 1 times 546. And I am getting 7,225. Okay, so this is now negative 97 is 97 plus or minus the square root of 7,225 over 2. Okay, and then I'm also on my calculator going to figure out what the square root of that is. So square root of 7,225 is 85. Okay? All right, where do we have to go from there? Yes, so do the equation. So what does that mean exactly? Yeah, right? So there's like an option here of plussing and minusing. So we have to figure out what those two options are. So x is going to equal 97 plus 85 over 2, which is 182 over 2, I think. Is that right? And that's 91. Or x equals 97 minus 85 over 2, which is 12 over 2, which is 6. Okay, so we got two solutions here. We need to answer this question of how long does it take Stuart to deliver the flyers alone? Yeah.
It can't be 6 because 6 is lower than 13.
Yeah, can't be 6 because if it's 6 minutes, then Lucy's time is negative. So this doesn't make sense in context. Doesn't make sense in context because now if his time is 6, her time is negative 7 minutes. That's not possible. So the answer to the question is this. X equals 91 minutes. Now, you need to go back and look carefully at what does the question ask, how long did Stuart take to deliver the flyers alone, and then how you assigned X. X is Stuart's time. So in this scenario, the answer is 91 minutes. But you will sometimes see X is Lucy's time. You solve for that, which is 91 minutes. And the question says, how long did Lucy take to deliver the flyers alone? And then you have to go through that process of subtracting 13. Okay? So really important that you go through that thing at the end where you double check what was asked for. So Stuart takes 91 minutes to deliver the flyers alone. Because we love in multiple choice to put in distractors, right? So I guarantee you that if this was a multiple choice question, 91 would be one option. 2 of the other options would be 6 and 78. Because 78 is Lucy's time, right? And if we ask for Lucy's time, you may, like people do the equation, they do all this work, they're like, oh, I got it, I see my answer, it's 91. But if the question asks for Lucy's time, then you still get it wrong, right? So it's got to read carefully and remember how you've assigned your variable. Okay, so far so good? Okay, so I think we'll get through one more today. And then we'll work on some more of these on Monday as well. And essentially, they're all sort of solved the same way. But I really want to expose you to the types of questions that you may see, because they do get very repetitive. And if you've seen them and recognize it, then you'll kind of understand the construct of the equation, which can really help to solve it. Okay, so Catherine burns 125 calories per hour more when she's running compared to when she's cycling. In one workout, she burned 690 calories on her bicycle and then 1,260 calories on her run. Her workout lasted 3 hours. That's a very long, intense workout. The table below represents this situation, and we are going to fill this out. Okay, and then we're going to use this equation over here, where x has to be greater than 125, to determine how many calories Catherine burns cycling. So I want to start with that. How many calories does she burn cycling?
690.
Oh, you know what? Okay, thank you. This question needs to be fixed. Because you're right, we know how many calories she burns cycling. We want to know how many calories she burns per hour cycling. Thank you. Otherwise, this question makes no sense. We want to know her rate, essentially. Okay? So let's start figuring out our chart. Now, if this is what we want to know, how many calories she burns per hour cycling, where do you think we should assign our variable? How many calories she burns per hour cycling? That's what we want to know. We got to put a variable somewhere in this chart. Yeah, let's put it in here. Because that's what we're trying to figure out. Okay? Now, once you assign a variable, you want to try and, in that same column, use that same variable to describe the other part to the situation, which in this case is her running rate, right? How many calories does she earn per hour running? Okay, now, how can we get some information in the question that relates those two rates together? Where do you see it? There's information that we're getting that connects the one rate to the other. Yeah. Yeah, and that's what you're going to say. So she burns 125 calories per hour more when she's running. So if this is x, what does this need to be?
X. Yeah.
We're going to use a different equation. Okay? All right. Now, what else do we know? We need to also put in one column of this chart needs to be information that's given to us in the problem. So what else can we plug in here? Okay, so does the 3 hours, though, connect to the running or the cycling? No. So you know what? But we're going to use that to build our equation. Yeah. But is there anything else that we can fill in?
Calories burned.
Yeah, she burns 690 calories cycling and 1,260 calories running. Okay. Now the third one should be built from the other two. So we have this little triangle, just like distance, speed, and time, that the rate is the amount of work done, divided by the time. Okay, so if we want an expression for time, how are we going to get that? Time is what? For rate. In this case, the work that she does is the number of calories that she burns. So for running, her time, work over rate, 1260 over x plus 125. Okay, and for cycling, her time is her work over her rate, 690 over x. Okay, now Maria mentioned we have to deal with this 3 hours thing, right? And that is actually how we're going to build our equation. When you start the equation building piece, you want to think, what is the information that I haven't accounted for yet in the chart? And in this case, It's that the total workout lasted 3 hours. Okay. So total is 3 hours. Total of what? Total time, yes. Her total time is 3 hours. Well, her time has been broken down into 2 pieces. The running piece plus the cycling piece. To get the total, we need to add those up. So the equation will be running time plus cycling time equals 3 hours. And I personally like to write the equation in this sort of half math, half English way first, because it really clarifies for me what each piece of the equation represents. Okay? So her running time is 1260 over x plus 125. Her cycling time is 690 over x. And that has to equal 3 hours. Okay? Now, let's think about our non-permissibles. Okay? So if you're just thinking about this as a normal equation, right, without a context attached to it, one non-permissible would be 0, and the other non-permissible would be negative 125. So those are our 2 non-permissibles. But because this x represents a rate, what type of number does that have to be? Positive, yes. So in fact, x can't equal negative 125 or 0, but because it has to be positive, x has to be greater than 0. And if x is greater than 0, it's not going to be negative 125 anyway. Okay, now I want to talk about why I crossed that other equation out. Because we could also use that equation to solve the problem as well. Okay? So the reason I crossed that equation out is that really when we made this cycling variable x, that was arbitrary. We could have made her running rate x, but then because the running rate is 125 more, we'd have to subtract 125 to get the cycling rate.
Oh,
so you have 2 options, right? This can be x and this can be x plus 125, or this can be x and this can be x minus 125. And one is not better than the other. Half of the people will do it one way, half of the people will do it the other way. And so that's why I wanted, as we were going through this together, I want to come up with this as a group. And if we as a group decide to assign that as x, I don't want you to start to think that the one that's given to you is wrong. They're both right. Okay? The difference is that if you solve for x in our equation, you'd be figuring out her cycling rate. And you have to add 125 to get her running rate. In this equation, you'd be figuring out her running rate, and if you wanted her cycling rate, you'd have to subtract 125. But there's often more than one equation that can be used to model a situation, and that's what's going on here. Okay? All right. Now, in terms of solving, I think I'm going to get you guys to practice solving this one yourself, because it's quite similar to what we just did, and we're also running out of time. So we only have a couple minutes left. I want you guys to finish this one out. I want you, over the weekend, to start to look at some of the questions in your booklet on page 44 to 46. Okay? There's 6 questions there. You may not be able to do all of them, but I want you to try and do a couple, because we're going to continue this work on Monday.